Chapter 26, RC Circuits, Lecture 2. A simple single loop resistor in series with a capacitor R and C connected to an idealized source of EMF. Idealized source doesn't have an internal resistance, so that's an ideal source. And initially the switch is open, the capacitor has no charge on it, and the current flowing is zero. When we close the switch, as soon as we close the switch, the charge on the capacitor increases and there will be a current flowing in the circuit. While the current is flowing, we can write down Kirchhoff's loop rule for the circuit. Just go around the circuit and write down the loop rule, and the loop rule will look something like this. So these are the sum of the voltages across components. That should add up to zero. But notice that the current I've written it as a lowercase I. Lowercase I means time-dependent current, and of course VBC is also time-dependent because it depends on the charge on the capacitor. VBC is the voltage between points B and C, that is the voltage across the capacitor. Now if I go back and write down these time-dependent values in terms of dq by dt, and VBC, write it as q divided by c, so I will be dq by dt, and VBC will be q divided by c. Just plug these values, plug these relations into our original equation, then our equation becomes a differential equation with variables q and t. So to solve this differential equation, we have to use the method of separation of variables. So we rewrite the equation, move one variable to one side, another variable to another side, and then integrate. So our integration would be, the integral on the left would be to do with dq, the variable dq, and the integral on the right would be to do with variable dt, and the limits of the integrals are for the time at the instant the switch is closed, time is equal to 0, and that corresponds to 0 charge at the capacitor plates, and after a time t the charge on the capacitor plate has reached the value of q. So these would be the limits of the integral. And the solution to the integral on the left is just natural log, and the integral on the right is just t divided by r. So we get minus c, natural log of e minus q divided by c equal to t divided by r. Divide both sides of this equation by minus c, and we get this equation. And remember, this equation, there are limits here, so the left hand side is between 0 and q, and the right hand side is between 0 and t. And then when you plug in the limits into the equation, you end up with the final value of the equation, final equation on the right hand side. And this final equation, as you can see, the left hand side is the natural log. So we'll take antilog from both sides of the equation, and the right hand side, when you take antilog, becomes an exponential function, exponential to the power minus t divided by rc. You then, on the left hand side, ln disappears, and you solve for the charge q. And when you solve and rearrange, this is the equation you end up with. Equation for the charge on the plates of the capacitor as a function of time. Now this equation shows the charge increases with time exponentially, and C times E is denoted by QF, is the final charge on the capacitor plates. Now it would be a good idea to examine the initial and the final charges on the capacitor plates. So initially at t equals 0, we just plug in 0 for t, and we get exponential to the power 0, which is 1. So in the parentheses you have 1 minus 1, which becomes 0. Therefore the charge, the initial charge, quite clearly is 0. And when the time is infinity, then we have exponential to the power minus infinity, which is 0. And what you have in the parentheses is just 1 minus 0. So the charge Q will be just EC multiplied by 1. So Q will just be equal to E times C, or the charge that we call QF. So now we can go ahead and graph Q as a changes of Q as a function of time, and get the exponential behavior shown on a graph. So as you can see, the final charge, capacitor, the charge and the capacitor will reach the final value QF at that point. So that is when it's continued and it reaches that value, and the initial charge is 0 at that point. There's a quantity of interest here that we call the time constant of the circuit, denoted by the Greek letter tau, and that is defined as the product of the resistance multiplied by the capacitance. So we can elaborate on that time constant a little bit more if we consider the equation and just consider setting t equals to the time constant. So Q will be equal to QF multiplied by 1 minus e to the power minus the time constant. So just plug in RC for t divided by RC. So RC divided by RC will give you 1. In other words, you have 1 minus e to the power minus 1 now, and e to the power minus. And if you just plug that into your calculator, you'll find that the answer to that is just 0.63 times QF. In other words, we can define the time constant as the time taken for the charge on the capacitor plate to reach 63% of the final value. And that on the graph is that point. That is in fact 0.63 of the final charge. So I draw a horizontal line and I find the intercept at that point, and then drop a perpendicular. You find that on the time axis you can denote one time constant, RC. It would be interesting to also note the potential difference between the plates of the capacitor, see how that changes. So if you go back to the equation, top equation, and divide both sides of the equation by C, then we get VBC, which is the potential, which is the voltage across the capacitor between points B and C. And that is just, as you can see, it just follows the same exponential increase as the charge. Exactly the same function. All right, next thing we are interested to find out is how does the current change with time. So let's look at the charging current. The charging current, we can start by using our equation for the charge and differentiating it with respect to time and we get the current. I is dq by dt. Just differentiate. And if you do differentiate, you can practice doing that. You should get this equation. So that is the current. And you get I naught multiplied by the exponential e to the power minus t divided by RC, which shows and the current flowing into circuit will decrease exponentially with time. And we can just go ahead and plot it. And the plot shows you the current decaying with time. And the initial current, of course, would be I naught when t is 0. At that point there, that would be the initial current, and decreases as the time goes on, exponentially. All right, it would be interesting also if I just show you part of the circuit. You can see the resistor and the capacitor in series, and the current is flowing through both of them. So that current, if I multiply both sides of the equation by R, I get the potential difference or the voltage between points A and B. That's VAB, and that will just be equal to E times exponential minus t divided by RC. In other words, but voltage across the resistor decreases exponentially while the voltage across the capacitor increases exponentially. Okay, next thing to consider is the discharging of the capacitor. So let's take a look at the circuit here. The circuit for a discharging capacitor is when the capacitor is fully charged. So we start off by a fully charged capacitor and the switch open, and then as soon as you close the switch, the capacitor begins to discharge, so a current will flow in the opposite direction to the charging current. And of course, you must take out the source of the EMF and then close the switch. So when you take the source of the EMF away, and notice that the initial charge on the plates is the same as the final charge of charging circuit, that is E multiplied by C, then you can just go ahead and write down the initial loop equation that we had and eliminate the EMF. We'll take the EMF out of the equation, and then knowing that I is a time-dependent current, so write I as dq by dt and write VBC. So write I as dq by dt and write VBC as q divided by c, and then you get an equation that tells you the time dependence. dq by dt equals q divided by rc. And as before, we want to solve this differential equation by the method of separation of variables. So you take dq to one side, and you take dt to the other side, and then next you integrate. Integral of the left-hand side is the same as the integral of the right-hand side, and then you just plug in the limits of the integral. Notice that when you close the switch at t equals 0, that corresponds to the initial charge on the plates of the capacitor, which is Q naught, or is E times C. And at a later time t, the charge has decreased to a value Q. So these would be the limits of your integrals. And next you have to solve the integrals, and the integral on the left clearly is a natural log of Q, and the integral on the right is simply T divided by RC. And then when you solve that, so you get an exponential function, that you can just plot it. So the plot shows you that the charge on the plates decreases exponentially as the capacitor discharges, and the time constant of the discharging current, of course, is discharging or the time constant of the discharging charge on the capacitor plates is the same as before. That is, the time constant is R times C, because nothing has changed. R and C are the same as R and C as before. Now, we are also interested to know, would be interesting to know, how does the potential difference, how does the voltage across the capacitor change as it is discharging? So take the equation, divide both sides of the equation by C, because you know Q naught is actually equal to EC. So if you divide both sides of the equation by C, you get VBC on the left hand side. That is equal to E multiplied by the exponential of minus T divided by RC. And that tells you that voltage across the capacitor follows exactly the same exponential function as the charge. So the voltage decreases with time exponentially, just like the charge decreases exponentially. Next thing to do is to take a look at the current, discharging current. So we start by our equation for charge and differentiate it with respect to time. So you get dq by dt simply is just comes straight from the differentiation, and it tells you that it is equal to the same expression we had for charging, but this time we have a negative sign here. The negative sign just indicates that the discharge current is in the opposite direction to the charging current. Otherwise it would have been positive. Alright, so now we can just go ahead and graph it. Take a look at the graph, and the graph shows you that the current is below the zero line because it's negative. And of course the same value as the time constant because R and C hasn't changed. And the initial value of the current will now be minus I naught at that point. So that is actually the end of the RC circuit. Be a good idea at this point to look at a couple of examples. So let's take a look at a capacitor that is connected to a resistor, and the capacitor is fully charged to begin with, and the switch is open. So when we have the initial charge of the capacitor given to us as 5 microcoulomb when the switch is open, and after we close the switch, the question is, how long does it take for the charge on the capacitor plates to reach 1/10 of the value of the initial charge? Because the initial charge is 5 microcoulomb, and the question is, how long does it take for it to reach 0.5 microcoulomb? That's 1/10 of the value. And part B of the question is asking you, what is the current at this specific time? Alright, so you're given the values of the resistance as 10 to the power 6 ohms, and the value of the capacitance is 10 to the minus 6 farads. So you can straight away figure out the time constant of the circuit, which is R times C, and that means 10 to the power 6 ohms multiplied by 10 to the power minus 6 farads, which will give you 1 second. That's the time constant, 1 second. Since the capacitor is discharging, of course you want to write down the equation for discharge. So you write down Q is equal to E times C e to the power minus t divided by RC. And what we need to do is to solve for t when Q is 1/10 of the value of the initial charge. The initial charge is EC, so when Q is EC divided by 10, we want to know what's the value of t. Alright, so just go back to the equation. Set Q equals to EC divided by 10, and that would be equal to EC e to the power minus t divided by RC. The EC cancels out, and you get e to the power minus t divided by RC to be equal to 1 divided by 10. Now it'd be much easier if I deal with a positive exponent. So I find the reciprocal of both sides of this equation, and that makes the exponent positive. So the reciprocal of e to the power minus t divided by RC is just e to the power plus t divided by RC, and that would be equal to 10. And now I take log from both sides, and then I get t divided by RC equal to ln of 10, and that will give me straight away the value of the time, which is RC multiplied by ln of 10. Well, I already figured out what RC is 1 second, so that would be equal to 1 second multiplied by ln of 10, and that will give you 2.3 seconds, and that is the answer for part A. Part B of the problem is asking you what is the value of the current at this specific time. So you write down the equation for discharging current, which is minus E divided by R. You don't have to write the negative, but just let's stick to the direction of negative direction. So minus E divided by R, e to the power minus t divided by RC. And instead of going and finding the value of E, which you can do, I already have the values that I want, so I multiply the right hand side of the equation, the top and bottom, by C, so I get minus EC divided by RC e to the power minus t divided by RC. Now I have those values. EC is just simply given is 5 microcoulomb, so it's going to be 5 times 10 to the minus 6 coulomb divided by, with a negative sign of course, divided by RC, which I figured out to be 1 second, and multiplied by e to the power minus 2.3 seconds divided by 1 second. And therefore current is figured out to be minus 5 times 10 to the minus 7 coulomb per second, or amperes. Let's take a look at another example. So in this example, you're given a circuit with 3 capacitors, 15 microfarad, 20 microfarad, and 10 microfarads. And you're asked to figure out the current through the ammeter here under 2 situations. Situation 1, just after S is closed. That means figure it out at t equals 0. B, long time after S is closed. That means when t is equal to infinity. Let's take a look at our basic equation and basic circuit, very simple circuit, the RC simple circuit. Alright, in this circuit, if I write down the charging equation for the current and consider t equals 0 and t equals infinity. At t equals 0, plug in 0 for the time, and you get I equal to E divided by R. Alright, E divided by R, take a look at the circuit. E divided by R really means at t equal to 0, the capacitor is shorted. In other words, instead of a capacitor, you have just a piece of wire, piece of conductor. And then part B, when t is infinity, just plug in infinity for t, and then you get e to the power minus infinity, you get 0. So therefore the current is 0 now. Take a look at the circuit. How can the current be 0? Only when the capacitor behaves as an open circuit. No connection. So from that conclusion, I can go and redraw the complicated circuit, considering with the consideration of all the three capacitors being shorted for part A and being open circuit for part B. And that's what it looks like. At t equals 0, capacitors are shorted. So, for example, consider capacitor, that capacitor, the 20 microfarad capacitor. If that's shorted, then you simply have a conductor there. But if you consider the 15 microfarad capacitor and you short that one, that means the 25 ohm resistor that is in parallel with it just disappears. The same thing applies to when you short the capacitor 10 microfarad, the 25 ohm resistor disappears. And therefore, that circuit simplifies to what I've drawn here, this circuit here. Notice that the 50 ohm and the 25 ohm, these two, are in parallel. So if that's point A and that's point B, I can just replace, I can just figure out 50 and 25 and find the equivalent value of the resistance, RAB, which comes out to be 16.67 ohms, and just between points A and B, just insert a resistor of the value of 16.67 ohms. So I end up with only three resistors, 75, 15, and 16.67, which adds up, those three add up to 106.67 ohms. So the current flowing through the ammeter would just be 100 volts divided by this value, which is 0.94 amperes. Next, apply part B situation, which means the capacitors are open circuit. Well, if you go back to the circuit and consider all the capacitors to be open circuits, you will see that the 25 ohm here and that 75 ohm just remain. But the 50 ohm here, when you open circuit this capacitor, the 50 ohm disappears because no current will pass through it. And of course, the 25 ohm here and that 25 ohm will add to 50 ohm. So that 50 ohm is the result of those two. And on the top you have 75 plus 25. And of course 15 ohm just remains. So now you end up with four resistors in series that you add because they add up to the value of 165 ohms. So you simply find the current. The current is just 100 volts divided by 165 ohms. And that's the solution. So seemingly a hard circuit, difficult problem, is really reduces to two simple circuits that you can figure out very easily. Single loop circuits. Okay, that ends the discussion of chapter 26.